In this module, we'll cover a brief overview on finite element analysis, also known as FEA. The goal of this module will be to review the finite element mesh types used by the Autodesk Moldflow products. Why do we want to do this? It's important to understand the mesh types and their capabilities because that's critical in order to use them properly. Just so we're all on the same page with our terminology, we'll cover what a mesh actually is, or define that. So a mesh is basically a division of a physical domain into a number of subdomains or elements. So basically we're taking your CAD part and we're breaking it into several small components, almost turning it into a puzzle, you could say. So these subdomains that we broke your part down into, we call those elements. We use these elements, there are several types. So one is a two-node linear element, which we see on the left there, it's a beam. Another one is three-noded triangular element, also commonly called a shell or a triangle. And then a four-noded tetrahedral element, which is used in our 3D mesh type. So those elements that we previously discussed all have nodes. So these nodes determine a coordinate position in space. There are also places for us to put boundary conditions such as injection locations, coolant inlets, vent locations, things of that nature. In a mesh, these nodes are basically at the ends of beams, either end of a beam, and at each point of a triangle or a tetrahedral element. Certain analysis results are recorded at these nodes, such as velocity, pressure, and temperature calculations, so they're very critical in the analysis. Now, this might not be very apparent for Autodesk Moldflow Advisor users, but there actually is a mesh in the background, or a meshing process that is automated in the background for you. So beams are used in Advisor for cooling channels and feed systems. And then for your part, you typically have a choice between a dual domain mesh or a tetrahedral mesh, or some call 3D. So what we'll do is explain this in a little more detail later on and why you might use one over the other. So here you can see an example of a dual domain mesh versus a 3D mesh. 3D mesh is typically more optimal for thick-walled parts or capturing complex flow fronts. So in this example, you can see the dual domain mesh is having a little bit of an issue maybe capturing that flow front on the top part, whereas the 3D mesh is not. Our dual domain mesh type is something that's proprietary to Autodesk Moldflow. Some also commonly refer to this as a 2.5D or 2.5 dimensional mesh. It's not a true 3D mesh in that we don't have elements and nodes through the thickness of the part to do our calculations at. However, we can still get profiled results and see what's going on through the thickness and offer a true 3D representation of that part from a geometric standpoint, as opposed to midplane, which is a single surface through the thickness. So with dual domain mesh type, we have connector elements that basically allow us to synchronize results from the top and bottom surfaces of the part. So as the flow front progresses through this part, we know we should keep it synchronized between or through the profile of that part. And that's what these connector elements help us do. They also have zero flow and heat resistance, so they're not affecting anything in that aspect. Now, the dual domain mesh type does have a few assumptions that we need to be aware of. So it is designed primarily for thin-walled parts. You may ask yourself, what's a thin-walled part? 9 times out of 10 you'll be able to take a look at that part and see. You know, in the lower right-hand corner here, we have that very large chunky model. We could very clearly see that that is not a thin-walled part. That's thick-walled. The one on the left, our snap cover, clearly a thin-walled part. So 9 times out of 10 you'll be able to do that, but if you do get into a situation, or maybe as a beginner you want a rough guideline, what we would typically recommend is the flow width should be at least 4 times the thickness. So if you can get it 10 times the thickness, that's even better. The reason we say this is because we're using the Healy-Shaw model for this. So what that does is we're assuming laminar flow of a generalized Newtonian fluid. Inertia and gravity effects are ignored. That's not such an issue or such a problem with thin-walled parts, but could be if you're trying to simulate jetting in thick-walled parts. In-plane heat conduction is negligible, thermal convection in gap-wise or thickness direction is neglected, and heat loss from edges is ignored. So the main thing to take away from this is that we're neglecting heat transfer on the edge of that part. So when you're analyzing thin-walled parts, that is negligible. However, when you get into these thicker-walled parts, you are ignoring heat loss through a significant amount of surface area on your part. So that can impact how our predictions or how we're predicting the part cools. So thin-walled parts, again, it's pretty negligible. Thick-walled parts, it's not a good idea to run the dual domain mesh type on. So for dual domain, the flow front growth, what we're doing is basically saying the flow front grows to connecting nodes from an injection cone. So if you look at our image here on the right, that number 1 dot is in yellow, that's where our injection cone is. That's going to be filled first, and then naturally we're going to grow outward to nodes 2, 3, 4, 5, 6, and 7 there. As those fill, the surrounding ones from them will fill, and so on and so forth. One thing we'll also want to take note of is that the melt temperature is homogeneous entering the mold. You tell us what the melt temperature is, and that's how it comes into the tool or into this injection location. And then we're also saying that the polymer freezes as it hits the mold wall. Now for tetrahedral mesh assumptions, we'll get into these a little more detail. So they're just, as we mentioned, the tetrahedral mesh or the 3D mesh is designed for thick and chunky geometries. We're using a full 3D Navier-Stokes model, which is solving pressure, temperature, and all 3 velocity vectors at each node through the thickness of this part. So that's what allows us to capture these complex flow fronts and what's truly going on through the thickness of the part. We're also seeing heat conduction in all directions, so we're not making that assumption that we're neglecting heat loss through the edge elements. We can also see inertia and gravity effects. So if you're trying to simulate special things such as jetting, then inertia and gravity can play a critical role there. Now you might say, why don't I run 3D all the time? The thing with 3D is that you're increasing your element count. So you shouldn't run 3D in every situation. If something is suitable for dual domain, then certainly run it in dual domain. It'll save you analysis time and model size, and it will reduce the hardware requirements you'll need to run that model. So 3D is not always the answer. So which of the following mesh type options can you choose from an advisor? A mesh is defined as a division of the physical domain into a number of subdomains, also known as elements. True or false? The dual domain mesh option is intended for thin-walled parts. True or false? When using a dual domain mesh option, heat loss is considered in all directions. True or false? A 3D mesh is suitable to be used on any part geometry. True or false?